The title of this presentation is CFD Methods and Variable Specific Heat. Oftentimes when you run a CFD simulation that includes the energy equation, you would like to account for the fact that your specific heat or the thermal capacity of the fluid that you're simulating changes significantly with temperature, or perhaps you have a multi-component system where the thermal capacity of each one of the components is significantly different from one another, and you would like to accommodate and account for that when you solve the energy equation. My name is Jeff Franklin. I'm the primary architect of Azore, a commercial CFD software package specifically designed to solve industrial level problems. I would encourage you to go to the website azorecfd.com to learn more about this software package. To start this discussion, we're first going to start with the general energy equation discussion, where the general energy equation is basically, we're going to say that we want to enforce the first law of thermodynamics for a system, where a system is a fluid system. And so this system basically has a certain energy level, which is this E value. And then Q really talks about the amount of energy that is added or taken away from this system, and W represents the work that's done on that system. And so our system is a fluid system, so we use a material derivative to kind of look at that system as it changes throughout space and time. So for a CFD model, we can kind of think about this system maybe in two different ways. One way would be to think of it as a system of particles that it has a certain amount of mass and a certain amount of energy that's traveling through space, and we watch and see how that mass changes, its energy states change as it moves from position to position. That's one way of looking at it. Another way is, from a CFD perspective, is to kind of pick a fixed space and watch these particles pass through that space. And the fixed space would be our CFD mesh, which is composed of many different cells. And we look and see how the energy changes as it passes through the cells and how the energy and the changes around that cell. And we use that to solve the first law of thermodynamics in our CFD tool. So if we take this system and we look at it in terms of an integral relationship, which is kind of the control volume method that is used for many CFD tools, this here we have basically our energy level as it changes with time in a particular control volume. Then we have this H, which is our fluid enthalpy. And we look at the mass and the fluid enthalpy, how it passes through the surface, so how the energy goes in and out of a particular cell. And then we have the thermal conductivity on the surface of a cell and the temperature gradient on the surface of that cell. And we can kind of use the temperature gradient and the thermal conductivity to get a feeling for how much energy due to this temperature gradient passes in and out of the cell. And then we have a source term, which could be like a combustion reaction or some other way of adding or taking away energy inside a cell. And that is kind of the way the energy equation is looked at from a CFD tool standpoint, where you have basically mass that's being moved around that has a certain amount of enthalpy, and temperature that kind of is used to look at the temperature gradient, or how energy moves due to temperature gradients. So, but now the enthalpy is the relationship between enthalpy and temperature uses the specific heat. And so this is the basic relationship where H is our enthalpy, Cp is, kind of the thermal capacity, a material property of sorts, and then our temperature changes. So changes in temperature multiplied by our specific heat gives us changes in enthalpy. And so we can kind of perform an integration of this differential relationship to kind of get an algebraic relationship for the enthalpy. And if we do that integration, we could kind of use a bounded one where we say, let's start at some reference enthalpy and go up to the enthalpy that we might be interested in, and then say, well, we're going to start at some temperature that we know, and then we're going to integrate it forward to some temperature that we don't know and that we might be interested in. And so we can kind of do all of that algebra, and what we're kind of left with is a couple of constants, this T reference and the H reference, that we really need to pick some sort of value for those. And 0 for our reference enthalpy is a common choice. It's a convenient one. And then another common choice for CFD tools is to pick, like an ambient temperature of 298 K. You could pick another temperature if you like, but most CFD tools choose this as a reference point and a good measure. And then what you're really left with is this algebraic relationship right here that relates the enthalpy to temperature based on this algebraic expression. So now we have used our specific heat to come up with an enthalpy relationship. So, but how can we get that specific heat into our CFD tool? And one of the common ways of providing information about how the specific heat might vary with temperature is to use a polynomial relationship, such as the one right here, where each one of the components kind of progressively temperature, temperature squared, temperature cubed. This is a nice, convenient, and common way of defining specific heat. And one thing about this relationship is that it is easily integratable. So once we have a relationship for the specific heat, we can simply integrate it and come up with yet a relationship for our H of T. So now we have an algebraic relationship for both our CP and our enthalpy. And so you provide this in the CFD software, it uses this relationship and it derives the enthalpy from the CP relationships that you provide. But if we have a multi-component system, then we need to account for the fact that the CP may vary between each one of these components, and a common way of combining and finding a mixture CP is to weight each one of the individual mixture component CPs with a weighting value, a mass fraction value, and you can kind of come up with a mixture equivalent for that mixture, where the weighting value is some number between 0 and 1, and the sum of all your weighting values for each one of the species in your mixture must sum to 1. So now that we kind of have a way of representing, kind of connecting together the specific heat, the temperature, and the enthalpy for both components or systems that have variation due to temperature or mixtures themselves. So we really have a good way of connecting and providing the information to the CFD solver so it can solve the energy equation with the awareness of variable specific heat. So let's just take a quick look at a typical curve, our enthalpy curve here, and I have taken two common components right here. Air is a common one, and here the red line represents the enthalpy changes of air with respect to temperature. You can see as the temperature rises, the thermal capacity, the enthalpy levels rise up. Now you'll notice water vapor is the blue line here, and here you can see that water actually holds a lot more energy per unit mass than air right here. And so now to kind of go back, if we wanted to know what a mixture enthalpy would be, for instance, if we had 50% air and 50% water vapor, then we would get this green line right here. And of course, it's halfway between the two. So our CFD solver, what it really does is it's constantly evaluating many points depending on the temperature distribution within your CFD solver along this line, giving it values, and then also along this line. But if you have a mixture, then it's also coming up with many different CP values between this curve and this curve, depending on the temperature that you have, as well as the fractions of each one of these components. So now we can really do a precise job of accounting for our specific heat. So let's just kind of think about these mixture systems a little bit more here. And the example I'm going to kind of choose for us to look at is a system where we have something that's happening upstream here, and we're getting combustion products from that system. They're at a high temperature, and they're composed of oxygen and water and nitrogen and CO2 and maybe a little bit of argon. And we want to cool that system down with dry air. And so just for this example, I'm just going to assume that the dry air is just O2 and N2. And we're going to assume really there's no reactions taking place in here. It's just kind of energy mixing, and we want to kind of look and see how the temperature changes and maybe what the mixed temperature is. And if we wanted to do that, and we could precisely do that, we would end up, we have 1, 2, 3, 4, 5 components here that we would need to kind of accommodate. We would probably have to solve 4 transport fields to solve this system for each one of these individual components using a CP for each one of these. And then, but really, if you look at this a little bit more closely, this is really one system. The combustion products, that is one system of energy that is coming into the system. And then we have one other component, which is our dry air, and that is also another system. So we really only have 2 systems. So perhaps there's a way to simplify this into something a little bit simpler to solve. And what we would do is we would kind of take this combustion mixture fraction, and we're going to say we're just going to treat it as all one mixture. And we can use those weighting values to combine together to come up with an equivalent CP that represents all of these weighted by each one of these components. And then we can also say we have another mixture over here that's composed of both oxygen and nitrogen, and we can combine those together, and this is our other mixture, which has a mixture fraction of 1. And so then we can change this system to this, where we only actually have to solve 1 transport field. And that would be the transport field either of the combustion products or the dry air. And so say, for instance, here, you would have something coming in at a high temperature, and the product's mass fraction would be 1. And down here, you have the dry air coming in. The products would have a mass fraction of 0, but the dry air would have a mass fraction of 1. So then we can basically solve for the mixture temperature. And the good thing about this is we have given up nothing. We're still representing the physics as if we had run every single one of those components, yet we have reduced the problem from 4 transport fields to 1. And not only that, is we don't have to trace all those other transport fields, and which would perhaps add a little bit more uncertainty in our simulation, because each one of those would have to be traced individually when we know that they are perfectly mixed. So let's think about this a little bit more. Perhaps we might have a situation where we would want to kind of keep track of the oxygen content downstream. And so we can also kind of keep track of that by recasting and creating 2 new mixtures. And this mixture is going to be kind of aware of the air. So we can kind of take this mixture and divide it into 2 mixtures. One mixture, which is basically 89% of the combustion mixture, and the other one, or 81%, and this one's 18% of just dry air. So what we've done is we've removed the oxygen and a portion of the nitrogen and created another mixture right here, which is still air, proportionally. But now we have a mixture that looks like this. So now when we go and run our simulation, we still only have 1 transport field. But in this transport field, our products on the inlet are kind of 80% products, combustion products, but also around 18% dry air. And then down here where we introduce our dry air, it's 0% combustion products, but 100% dry air. And then we can and then that allows us to also not only calculate our equal, our equivalent mixture temperature, but it will also allow us to calculate and have kind of a representation of the amount of air and oxygen that you might have, as well as maybe the distribution in that mixing process right here. So once again, we have reduced this problem from a 5-component system where we had trace 4 scalar fields to a 2-component system. So now we've kind of done this, but I think it's worth really kind of exploring and looking at this temperature energy relationship here. And if we look right here, the energy movement, like the heat flux through a particular surface, is really kind of composed of 2 things, where you have basically mass crossing the barrier with a certain amount of enthalpy, and that represents a certain way energy can cross over that surface. Or you have right over here, you have your thermal conductivity and a temperature gradient, which represents, how much energy might pass through that surface based on a differential in temperature. So the energy movement is really dependent on these 2 factors here. And it's important to realize that the temperature here, we're not solving for conservation of temperature. We're really using temperature to help characterize each one of these things. The temperature helps us characterize the enthalpy level we might have and the energy that we have there. And it provides a mechanism for calculating heat fluxes between where there's a temperature gradient, but we're never really conserving temperature in itself. We're always conserving energy, and the temperature is really just kind of a mechanism for us to keep track of the energy in their energy states. And it's easily relatable too, because we're we're very aware of temperature in our day-to-day life. So now we've kind of talked about the energy equation, how the CP is important in enforcing conservation of energy, and how its variation influences that conservation of energy. But it's important to remember, kind of on a secondary sense, when we run with a turbulence model, the CP actually plays a role in that as well. And so let's just kind of take a look of how the CP plays a role when you run your model as a turbulence model. And the first thing we're going to do is kind of look at the diffusion, kind of the conduction of energy between 2 points. So this would be within your domain. This is a cell, and this is a face between those 2 cells. And we're kind of looking at the thermal conductivity between these. How is energy going to move between here and here? And that really becomes dependent on the thermal conductivity that we have there. But when you're running a turbulence model, there's a lot more going on here. You have unresolved eddies, and you have turbulence that is kind of promoting additional mixing between these 2 points. And the typical way of accounting for turbulence between these 2 points is to come up with a new, what is often referred to as an effective thermal conductivity. And what this effective thermal conductivity is it's a sum of the laminar thermal conductivity plus a correction due to turbulence. And this correction looks like this, where it's composed of, right here, this mu t is the this is the turbulent viscosity right here, and the turbulent viscosity is really kind of a measure of the mixing potential there. And then we multiply it by our local CP, and then we divide by the turbulent Prandtl number, which is a constant for turbulence models. And so you can see here that the CP, like if we just think about our 2-component system on those curves of air and water, you can see that this correction right here is going to be greater for water than it would be for air. So it does play a role. Oftentimes diffusivity, it plays a secondary role, especially if your system that you're looking at is primarily convection or yeah, convection dominated, where you're just moving mass from one point to the other. But other times it can make a difference, and it's important to be aware that that's variable specific heat that you input there also appears when you solve a turbulent case. Now, when you go and look at for your turbulence model, when you get to the near wall, it's a little bit more complicated there, but the CP also plays a role there. And so here, let's just take our relationship. Here's a schematic here. So we have our wall right here, and now we're looking at the temperature gradient between the center of the cell and the wall, the boundary, this solid surface right here, and we want to account for the thermal conductance right here. And here, the structures, the flow structures here are much more complex because the temperature gradients could be very steep through here, the velocity gradients could be very steep through here, as well as your turbulence quantities are changing very rapidly as they start falling off due to the wall. So there's a lot more going on there. So the relationships, as you might expect, are a little bit more complex to kind of accommodate, since we don't typically fully resolve all of what's going on there. And so over here is a typical heat flux relationship here, and you see your dT, dN. This is our normal temperature gradient here, but this is the effective viscosity, and it has a similar form for what we were looking at before. We have your Cp, you have your laminar viscosity multiplied by this Y plus number and this T star number. And let's just talk about those numbers just briefly a little bit. Where we have our T star number this is a blended relationship. There are many different relationships that are used for T star. Here is a blending relationship where this relationship, when your Y plus is a kind of a small number, like on the order of 1, this term will dominate, or if it's a large number, say 30 or 100, then this over here, we would use this empirical relationship. The law of the wall would be used. And so all of these together kind of give us the relationship that accounts for all of the physics that are happening right here. And you can see this Prandtl number in itself is dependent on the variable specific heat that we have input. And it also is dependent on some other properties as well, as say, for instance, your viscosity of your fluid, the laminar thermal conductivity of the fluid. This is your Y plus number, which is also dependent on the density variation, your Y, which is the distance between here and here, and this is the shear velocity, which is kind of a representation of the velocity magnitude that's shearing down in this area, and then the laminar viscosity again down here. So all of these all combine together to give us this effective viscosity, and you can see that our specific heat that we input in plays a pretty significant role. And on the wall, actually the other parameters that you might put in for viscosity and thermal conductivity could also play a role in how this blending function is used. So in summary, we've kind of looked at a lot of different things. First, we looked at the first law of thermodynamics. How is the energy equation relationship connected to the CFD tool? We've reviewed how the enthalpy and the specific heat relationships and how they characterize and use temperature to enforce energy balance. We've reviewed variable specific heat. We've looked at typical temperature dependence expressions. We've looked at mass fraction dependence expressions. We've discussed a simple mixture of air and water. We've reviewed surface heat fluxes and how the temperature is really connected to the enthalpy and used to solve our energy equation. And then we've reviewed some turbulence impacts of how the specific heat also influences our turbulence predictions. So that kind of concludes this discussion. Um, I would encourage you, if you were interested in more technical content like this, please go to the YouTube channel right here at YouTube with Azore CFD. Or if you're also interested in some more technical content or to learn about AzoreCFD.com, is a great place to go to learn more about this tool.